Okay, hi everyone. Yeah, let's get started. So I guess today we're going to continue to talk about the implicit regularization. So last time we have talked about the implicit regularization of initialization. And today, this is last lecture. Actually, last week, in the last two lectures, we have talked about implicit regularization of initialization. And today we are going to have two parts. So one part is we continue with the implicit regularization. And this is a better characterization in certain cases, as I will describe more. And another is that we are going to talk about classification problem. In all the past few examples, we are talking about a regression problem. It turns out that for classification problem, the behavior is a little bit different. And you instead of like converging to some minimum norm solution, you converge to max margin solution, which is in some sense similar, but not exactly the same to the regression case. I guess with this lecture, we're going to conclude the discussion about the implicit regularization of initialization. And then next lecture, we're going to talk about the stochasticity. And that will be the last lecture about the implicit regularization. So, okay, so today we're going to have, so the first part, this is number one, number two. So the first part, we're going to talk about a more precise characterization in a certain case about the implicit regularization effect of initialization. You can see exactly how the initialization influenced the regularizer. And to have some preparation for today's lecture, we are going to talk about the so-called gradient flow. I was trying to avoid this notion in the past, but I think the spirit has shown up in the past as well. Like, so basically this is gradient descent with infinitesimal gradient descent with infinitesimal learning rate. So and the reason why this is useful is because in certain cases, we have infinitesimal learning rate, you can ignore some of the second order effect from the learning rate. And so this is just to make the analysis much simpler. You don't have to say how small the learning rate is. You don't have to deal with the second order effect because the second order effect is just literally zero. There's no second order effect. And the way to do this is that it's actually also kind of a pretty clean formulation of optimization, even though it's continuous time. So what you do is you say you have a loss function. Let's say LW is the loss function. So if you do gradient descent, then what you do is you say you take WT plus 1, and now I'm using the parentheses for time because I'm going to use that for the continuous time. So WT plus 1 is equal to WT minus eta times the gradient of the loss at time t. This is what you will do with gradient descent. And if you scale the time by eta, what do I mean is that now currently when you do gradient descent, every time you increase the step counter by 1. So before the time is t, and now the time is t plus 1, right? So, and now suppose you don't do that, you change the time scale. You say every update I only advance the time counter by eta instead of by 1. So what I'm going to get is that I get w of t plus eta is equal to wt minus eta nabla L wt. And these two processes, if effectively are the same, it's just that the unit of time changed by a factor of eta or 1 over eta. So, and now if you scale the time, then you can take eta to go to 0. So take eta to go to 0, and then this becomes a differential equation or kind of like a continuous process. So you can write this as wt plus dt is equals wt minus eta gradient L wt. I guess depending on what kind of community you come from, like you can also write this as wt dot, right? This is the derivative with respect to I guess, sorry, I think here you also replace eta by dt. This is how you take the eta to go to 0. And this is effective saying that the gradient, so that the derivative of w with respect to t, which we denote by w dot t, is equals to minus gradient L at w at time t, where w dot t, this is just the derivative of w with respect to the time t. So, and in some sense, this allows us to ignore the eta square term. And because eta squared here becomes dt squared, which is 0 compared to dt. So that's why this is useful. This will be useful for us. Like this, in some sense, this is mostly to simplify the equation. Like all the technical meat in some sense are the same. It just makes the analysis cleaner. And for the next two examples, in both of the examples, I'm going to use this gradient flow formulation for gradient descent. Okay, so now let's talk about the model we're going to discuss. So the model is a variant of the last lecture. And there are some reasons for changing the model a little bit. I'm going to discuss that, but it's not super important. So the model we're going to do is that you have some quadratically parametrized linear model in some sense, right? So we have two parts. Let me write it down. So you have some vector w plus, and you take this O dot 2 minus w minus O dot 2 transpose x, where we use this notation x O dot 2 just means x O dot x, and this dot O is the this anti-wise product. So w squared minus w minus squared transpose x, and w and w minus, these are both vectors in RD, and you can write w as the concatenation of w plus and w minus is the parameter. So basically, this is very similar to what we did last time. So last time we had something like f beta of x, which is beta O dot beta transpose x, right? So basically now you have a negative term in it instead of just positive. And the reason is there are two reasons. So there are two benefits compared to last time. So they are not super important, but let me anyway mention it. The one thing is that this f beta, so this model last time can only represent positive linear combination. Of x. And now this fwx can represent any linear model. Right, because before, if you take the anti-wise product of w and beta and beta is always positive or non-negative, so you can only have a non-negative linear combination of the coordinates of x. And now it can have like a negative coordinates. And another benefit is that like now if you initialize w plus 0 at time 0 to be equal to w minus at time 0 to be the same thing, then as you can see, fw0x is equals to 0. And I guess for every x, just because the positive part cancels with the negative part. And I guess you have seen this kind of things before. This is mostly for convenience. So this will make the analysis even more convenient because initialization has a 0 functionality. And we have, kind of like use this for the NTK, and this will be useful for our analysis. And actually, what we are going to do today is that with this thing, we're going to see that if you change initialization, actually you're going to get different regularization, and you can precisely characterize how does the regularization depends on initialization. And in one of the cases, it will be the NTK. In the other case, it will be similar to what we discussed in the last time. So yeah, maybe I should mention that. So okay, so and continue with the setup. So the loss function, the L height W will be, that's the square loss. And we can consider initialization as we discussed. We'll consider initialization W plus 0 is equals to W minus 0. So that's, you get the 0 initialization as the functionality of the initial model is 0. And also, for simplicity, we choose this to be alpha times all1 vector. And alpha is the thing we're going to change. We're going to see that how does the regularization, implicit regularization effect depends on the scale of alpha. So when alpha is small, it gives you something. When alpha is big, it gives you something else. And this all1 vector is kind of like chosen as before. In the previous lecture, it's chosen somewhat for convenience. You can still do it with other initialization. It's just that the form will be a little bit more complicated. And you can also have this. We can also have this theta space, right? So suppose theta corresponds to W plus. So let's say theta W is defined to be W plus to the power 2 minus W minus to the power 2. This is the actual linear function you compute, the linear function of W, right? So, and we can define, and we are interested in what kind of like linear model we are learning eventually, right? So let's say W infinity, let's define this to be the limit in time infinity. So this is how the Green flow, where the Green flow converges to, and let theta sub alpha infinity, and I think sometimes we just call this. This is the basically W, the model corresponding to W infinity. So this is the coefficient that we care about, right? We care about when you converge to infinity, what's the corresponding theta you get, right? So what's the property of this theta? And sometimes we just call it, for simplicity, we just write theta alpha. And omit the infinity, but this is the where we convert this to. Okay, and for the sake of the simplicity of the lecture, we assume everything kind of have a limit, so on and so forth, right? So all the regularity conditions are assumed to be met. Okay, and also just to set up some notation, let this X to be the data matrix, and this is the matrix in N2D, and let's say Y vec is the label matrix, label vector. Okay, so now here is the theorem that characterizes characterize the implicit regularization. Let me write it down and then interpret. So for NA alpha, so assume that you converge to a feasible solution. So assume that to a solution that fit the data. So in the sense that X theta alpha is equals to Y vec, right? So this is, if this is satisfied, it means that we fit the data exactly. And I'm using a purple color for this is because I don't feel like this is necessarily have to be an assumption. You can prove this actually. The paper did assume this in the theorem, but I don't think that you have to do it. And actually, I just checked with one of the author 2 days ago, and he also thinks that you don't need it. But this is not formally stated in the theorem. So I assume, but I do strongly believe that you can prove that you can converge to such a feasible solution. You don't necessarily have to assume it. But anyway, let's assume it, just so that we are consistent with the paper. And by the way, this is the paper by Wood. I guess I'll probably add the link to Woodward in 2020. I think the title of the paper is something like Rich and Kernel Regime. I don't know. I'm forgetting what's the Rich and Kernel Regime in over parametric model. So it's a pretty recent paper. It just showed up like 2 years ago, 1 year ago actually. So and so suppose you suppose you have this, then we know theta alpha is not only a feasible solution, it's not only zero order solution, but also it's actually the minimum norm solution or minimum complex solution according to the following complexity measure. That is the minimum complexity solution. So you take the arc mean over theta such that x theta is equals to y. So among all the feasible solutions, you will try to find the minimum complexity where the complexity is defined by Q alpha. And what is Q alpha? So Q alpha is a function of alpha. So the complex measure does change as you change alpha. And Q alpha is equals to alpha square times, the alpha square doesn't really matter because it's a scalar when you do the arc mean, times some function of each of the coordinates, Q of theta I over alpha square. And what is this little q? This little q is a one-dimensional function where this little q is a function that maps R to R, actually maps R to R non-negative, I think. And QZ is equals to something that I don't expect you to interpret, but I think we're going to look at special cases which we can interpret. So this arc Sanj, I guess it's pronounced as Sanj, right? In US, or Shine, Sanj. Okay. Anyway, arc Sanj, sine hyperbolic, right? So 0/2. I think in UK it's called Shine. I don't know why. Anyway, yeah. Okay. So all right. So okay. So the first order bit is that even though you didn't minimize this complex mesh in the algorithm, you only run gradient descent, somehow you find a minimum complexity solution, and the complexity is defined by something like this, right? So and now let's try to interpret. This is the abstract theorem, but the important thing is that in particular, when alpha goes to infinity, so if you have a very large centralization, then this complex measure Q theta alpha, this is something like theta I alpha square. It's something like theta I square over alpha to the 4. So which means that the Q alpha theta is something like I guess 1 over alpha square times the 2 norm of theta square. So basically, if alpha goes to infinity, then the so-called complex measure, the Q alpha, is the L2 norm of theta. And so, and if alpha goes to 0, then what's the complexity measure? So the complexity measure is, what's this regularization effect or complexity measure? This is Q theta I over alpha square. This is roughly something like theta I absolute value over alpha square times log 1 over alpha square. I don't expect you to verify this limit because you have to do some kind of like Taylor expansion to see this, but this is the thing. So then this means that Q alpha theta is in some sense the 1 norm of theta, I guess over alpha square times log 1 over alpha square. But the constant doesn't really matter because It doesn't change the order of this of the different theta.
One thing about your infinity is cube theta I alpha squared is approximately theta I squared.
Oh, sure. That's, that's what I mean. Yeah. Cool. So basically this is okay. In summary, when alpha goes to infinity, then this is minimum L2 norm solution in a theta space of theta, and an L4 norm for the W, right? Because theta is the square of W. And when alpha goes to 0, this is similar to what we discussed the last lecture. So you have the minimum L1 norm of theta, which is the minimum L2 norm of the W's. So this regime is what we have seen in the last lecture, and with a very similar model, right? So but this characterizes the whole regime, and there's and between alpha and 0, you basically have interpolation, some kind of interpolation between L1 and L2 regularization. So that's why this is more precise than before, right? So you know how does things interpolate. Of course, it's kind of like for any particular alpha, this Q function is a little bit complicated, but it's just the sum, kind of like sum of like some power of theta I in some sense. But the power is kind of between 1 and 2. You can kind of think of like that, but it's not exactly a power, but it's something like that. Oh, okay, say it again. Yes. Alpha is the scale. So this is the only thing that depends on alpha in the algorithm. So we say that the initialization is alpha times all-one vector. And this all-one vector, actually, you can change it as well. I think if you change it to an arbitrary vector, for this regime, for this case, you actually don't change anything. So for this limit. So for the other limit, I think you change a little bit because the L2 norm becomes weighted by the initialization, by the particular initialization, if it's not all one vector. If it's all one vector, the weighting is just all the same for all coordinates. If they are not all one vector, it's not all one vector, then you have a different weighting. Yeah, those can be found in the paper. I just, for simplicity, I didn't show the exact weighting. Right, and so here are some intuitions about this interpolation, and in some sense, just to connect to what we have discussed. In some sense, this is kind of like you can view this as a unification of what we have discussed, like in the past few lectures. When alpha is small, this is small initialization. So so this is basically similar to the previous case, a similar intuition to previous lecture. And but there is a small thing. So a small note is that it's not exactly. So this is only when you have when you go to the limit, right? So you have the minimum L2 norm solution. But when alpha is not 0, it's not exactly minimum, like the regularization effect means the regularization effect is not exactly closest solution to initialization. I think this the paper shows there's some tiny differences in some sense. So only when alpha goes to 0, you can basically say this is the closest solution to initialization. But generally, this is something we have kind of discussed last time. And when alpha goes to infinity, actually, this is indeed the NTK regime. So and why this is the NTK regime, I'm going to show you like this is kind of similar to what we have discussed before, but let me just do it again. So why this is the NTK regime? So let's look at recall that in the NTK regime, we have this so-called two parameters, sigma and the beta. So beta there was the smoothness or the Lipschitzness of the gradient. And this is the condition number. Right, and we say that, and recall that we had this discussion that sigma beta over sigma square matters. Right, so if this goes to 0, then you are in the NTK regime, you can approximate that quadratic. And now let's compute what sigma and beta is in this case. So the gradient with respect to the initialization x, so W0, W0, let's take this to be alpha all one vector. It's W plus and W minus, be both all one vector, alpha times all one vector. And we can compute the gradient at initialization x, right? So there are two set of parameters, right? So the gradient for the W plus, I think you can, if you compute, is something like this. And the gradient for the W minus is just this. Oh, sorry, this is element-wide product. You can do this easily just by chain rule for every dimension. And this is just equals to, I guess there's a 2 factor 2 here, which I oftentimes probably forget. And this is 2 alpha, because these two are just all one vector. So this is 2 alpha x minus x. Something like this. Right. So, and now you can see that sigma and beta both linearly depend on alpha. Right. So what is sigma? Sigma is the condition number of this. Sigma is the condition number of the gradient matrix, right? The feature matrix that consists of the gradient for every data point, and the condition number scale linearly in alpha. Right, and beta is the Lipschitzness, which also scales linearly in alpha, just because alpha is multiplied in front of the gradient. So both of these scales linearly. So that's why beta over sigma square will converge to 0 as alpha goes to infinity, because below you have degree 2 dependency on alpha, and in the denominator you have degree, in the numerator you have degree, like you have a linear dependency on alpha. So that's why this whole thing, goes to 0 as alpha goes to infinity. So, and also, like when alpha goes to infinity, this is the NTK regime for the trivial feature, because now the x of phi of x is this thing. Its feature map is really just literally this, right? This is just literally the trivial feature, because the only thing you did is that you flipped the x, which doesn't really make any difference essentially. So basically you get the minimum norm solution. So you get so if you believe in the NTK perspective, you should get the minimum norm solution. So the NTK perspective will also tell you that you get minimum norm solution. Like according to the features, right? Minimum norm solution, minimum L2 norm solution using the feature, basically x minus x. And x minus x is, in terms of a feature, that is not very different from x itself. So basically you just get essentially the minimum L2 norm solution for the linear model. So that's the same as we discussed, like the same conclusion as we discussed above. Any questions so far? So the question is, why NTK give you the minimum norm solution? I think this is just because when you do the kernel method. So when you use kernel method, so NTK tells you that you are doing kernel method with certain feature, right? So NTK means kernel method And the feature just turns out to be this trivial feature. And kernel method with the feature just give you the minimum norm solution. That's what the kernel method does. So because what kernel method does is that you like that's just what the kernel method do. Like when you don't have enough data, when your kernel, like when you feature dimension is bigger than the number of examples in the kernel method, you are learning the minimum norm solution for the features. Because otherwise, you have to define something, right? So like the kernel method, everything is L2, so you are minimizing L2 norm. That's implicitly in the kernel method. Yeah, that doesn't depend on initialization because it's a convex problem. And you use a particular algorithm when you do the kernel method. That kind of algorithm gives you the minimum norm solution. Okay, cool. So, okay, any question? More question?
Alpha going to infinity, that's the perspective seems like it could lead to all sorts of problems in a kind of optimizer. But I guess like from a theoretical perspective, it's interesting to analyze it because you could say that then minimizes
Yep. So I guess in some sense repeating the question and also answering it. So when alpha goes to infinity, so yes, so your problem will be very ill-posed. In some sense, like the optimization landscape will be very bad, just because your function will be not very smooth. So and this part is hidden here because you are using gradient flow. So you are using infinitesimal small learning rate. So that's why it's hidden under it's swept under the rug. And then practically, you also don't necessarily want to use the large learning rate. For one reason is the optimization, and the other reason is that maybe the L2 norm solution is also not good, right? So like you have an L1 regularization, at least for this particular setting, right? So that's another reason why you don't want to use very large learning rate. Very large initialization. And another thing is that in practice, people sometimes do use, like this is about the empirical setup, when like sometimes people do use large initialization, but people don't use infinitesimal small learning rate. So then you still cannot get into the NTK regime. But that's a good thing because you don't want to go to the NTK regime. So that's why at the beginning some people have confusions, because at the very first paper by this NTK paper, I think they are claiming that initialization scheme they are studying is actually what people do in practice, and that's kind of true. That's kind of, it's very close to the Kaiming Hertz initialization or the Xavier initialization. So in terms of the scale, but because they are using very, very small learning rate, so it's actually not really, the theoretical setup requires very, very small learning rate. But empirically, you don't use those small learning rates. And also the theoretical setup doesn't have the stochasticity. So all of this together, it makes the theoretical setup different from the empirical setting. And that's a good thing, because the theoretical setup says that you don't really do anything super different from kernels. Okay, so now let's discuss the proof of this theorem. So I don't have there is a little bit kind of like this proof is kind of interesting in the sense that the proof is similar to the linear regression model, similar to the linear regression proof, but not similar to what we discussed last time, not similar to last lecture. Right, you would probably guess this is similar to last lecture because the last lecture has almost the same model as this one, and is only doing a subcase of this, right, when alpha goes to 0. But it turns out that the proof is very similar to the linear regression one, and you have this two steps. The first step is that you find the invariance. maintained by the algorithm, by the optimizer. And recall that this invariance was that theta is in the span of xi, right, for linear regression. This was like probably like 2 or 3 lectures ago when we analyzed the implicit regularization effect of initialization for linear regression. We say that because you initialize at 0 and use gradient descent, you're always in the span of the data. And here we're going to find a different invariance, which is more complicated. And it's even harder to express, but we're going to find the invariance. And then you use the invariance. So step 2, like a kind of like, in some sense, characterize the, I guess characterize is a very vague term, but characterize the solution using the invariance. So in some sense, use the invariance as additional information, right, to pin down which solution you converge to, right? In some sense, the difficulty is that if you, without any additional thing, you just know that you converge to a 0-error solution. You don't know which one you converge to, and the invariance tells you that which one you converge to, and the invariance depends on alpha. So, and there's nothing about population versus empirical. Like everything is empirical here, right? I didn't even define where the data come from, right? I only tell you that this is the minimum norm solution such that the empirical error is 0. I don't have to care about population at all. So yeah, how does this kind of techniques compare with the techniques we discussed the last time, where you use the fact that the data, the empirical loss concentrates around a population loss in certain region, and you somehow do some kind of like control of the dynamics. I don't know how it's kind of hard to compare. Like these are 2 different approaches. There's some good thing about this kind of approach because this doesn't require population. That sounds a good thing. But the bad things about this approach seems to be that it's very hard to find an invariance for harder models, or like for more complex models. The invariance, you will see the invariance is a little bit kind of magical somehow. But that said, for more complex models, even the previous approach, the approach we discussed last time, wouldn't work either. So it's hard to say. Anyway, so let's proceed to see how does the proof work. So we need a little bit notation to somehow simplify our expression. So let's say let this x tilde to be the extended data matrix. So you extend the matrix to, this is to deal with you concatenate x and minus x so that you get n by 2D matrix. And sometimes this is just to try to write everything in matrix notation so that you don't have to have the minus thing. So we will take WT to be the concatenation of W plus T and W minus T. This is of dimension 2D. And let's take WT O.2. I guess we say that this is the n2s power of WT. And this means that with this notation, x tilde times WT O.2, this is x minus x times W plus T 2, W minus T 2, and you can verify this is really the same as this is just what the model computes. Right, this is the model output on the n data points. So I just want to use this so that you have the matrix notation, and now you can compute what's the derivative like of t was W dot t, right? This is the gradient because we are doing gradient flow, so this is equals to the gradient of L I time t. And what's the gradient of L I time t? This is gradient of this loss function, and now can be written as, I guess, the loss function of WT now can be written as x tilde WT O.2 minus y vec 2 norm square. That's because I vectorize everything. So let's copy paste here. And then I take the gradient. Taking the gradient, you can use the chain rule. So if you believe me that I got the right chain rule, so this is x tilde transpose RT entry-wise times WT, where RT is equals to x tilde times WT O dot 2 minus y back is the residual vector. So if you are familiar with linear regression, you will realize that this is kind of like, this is what you got from the, so this is the, if it was linear regression, if it is a linear regression, then this term will be our gradient. But now it's not linear regression because you have the quadratic parameterized model. That's why you also have to do chain rule to look at the derivative of the quadratic of WT. That's why this is because it's quadratic. Anyway, so if this is just one way to think about why this is true. But the formal verification would be just that you do chain rules for everything. Oh, sure. There should be I think there's a 2 here, right? Wait. Let me see. I think I wanted to make a 2. So that means I think my loss function should have a half. So where's my loss function? Okay, the loss function is a half. I guess I also define a loss function somewhere else before. Here. Right, that sounds good. I mean, like my brain just automatically remove all the constants. So it's very hard for me to deal with this. Okay, cool. So, all right. Okay, so now, how do we kind of like we said that we want to have some invariance for this in some sense, right? So we want to somehow solve this differential equation, but you cannot really solve it exactly. This is I'm not an expert on solving differential equations, but I think this is beyond the scope of like this is something you cannot really have a closed form solution. But interestingly, you can get something without solving it exactly. So we claim that. So actually, this is in a paper they just say they claim it's easy to verify this. You can claim that WT satisfies the following. Satisfies this times exponential minus 2x tilde transpose T RS ds. Okay, why this is the case? So first of all, this is not a solution. This is not depending on what you mean by solution. This is not necessarily in my definition of closed form solution because RS still is a function of W, right? So but it's going to be something very useful for us. And why this is true? It's actually relatively simple, but so here is the reason. So this is because what you can do, suppose you have a like a differential equation, something like u dot t is equals to vt times ut. So I'm trying to abstractify it a little bit so that I can give a clean analysis. So you can see that this is a good abstraction of what we had before, because before on the left-hand side you have the derivative of w, and on the right-hand side you have something times w itself. So this will be u, this will be v, this will be u, and this is u dot t. Right, that's my abstraction. And then suppose you have such a thing, then you can always do the following. You can say that u dot t over ut is equals to vt, right? That's always true. And then the left-hand side, this is one of the magical thing in many cases, like this is log of the derivative of the log of ut. Just by chain rule. I think probably have seen this in other contexts like policy gradient in other cases, depending on whether you know any of those. But anyway, so and then you can integrate both sides. So you can say if you integrate, you get log of ut minus log of u0 is equals to the integration of the right-hand side, like this. And now you remove the log, you get the exponential. So ut over u0 is exponential times integration of this. And now, if you map u to w and v to this, I guess u to a coordinate of w and v to be a coordinate of this x transpose r ti, then you can apply this and you get the desired result. And by the way, I think I need to make a remark here that this is entry-wise application of exponential. So this is a vector. This is another matrix. So a matrix times a vector, this becomes a vector. And you take entry-wise exponential and you take the entry-wise product with W0. Okay, any questions so far? So now let's see why this is useful. It's a little bit magical in my opinion. I don't have a conceptually, I think this is fun, but I think the proof on the proof level is somehow there's a little kind of like either you can call it coincidence or magic. So there turns out that this is all you need to verify this is a good solution. This is the minimizer of the solution. So first of all, we turn this into something about Stata. Right. So now we have a characterization for W, and let's turn it into something about Stata. So recall that, and also we simplify this a little bit. Recall that W plus 0 is alpha O1 vector. W minus 0 is alpha times O1 vector. So that means that W0 is also O1 alpha times O1 vector. This is in 2D dimension because W is a concatenation of W plus and W minus. So that's why this thing W0 is basically not important. You just have alpha. So and the theta t, so the theta at time t is W plus t power 2 minus W minus t to the power 2. And this will be okay, let's use this formula. Let's use this formula. Let's call this 1. Using 1. So the W0 doesn't matter, right? Only thing it contributes is alpha. So we get alpha squared. And so, I guess I'm not sure. Let's see. So maybe I'll just do this small calculation here. So x tilde transpose is x transpose minus x transpose. So that's why exponential minus 2x tilde transpose some vector v will be this integral. So this will be a vector like so let's say suppose you take this to the power of 2, then this will be exponential minus 2x transpose v, because this part is from the first part, and exponential minus 2 minus times 2x transpose v, and then to the power 2. Okay, so and then this power 2 will become 4 because this exponential, so you get exponential 4 minus 4x transpose v, exponential for x transpose b. So this small derivation is trying to deal with this. So you know that this thing to the power 2 will be something like this. And then the first part corresponds to W plus, and second part corresponds to W minus. So that's why you get something like here, W plus square will be exponential minus 4x transpose this, and minus exponential 4x transpose this. I guess what I'm doing here is just trying to make you believe that this derivation is true, but it should be trivial derivation. There is nothing like difficult. So, and okay, so this is the characterization of theta, and you can see that this is this exponential of this minus exponential of the same thing. You can write this more succinctly as the sinh for x transpose. This is just a better definition of the sinh. I think sinh is something like exponential t plus exponential minus t over 2, something like that. So, okay, so basically we have a characterization of theta. And, right, and then you know that the theta alpha, right, is equal to theta alpha at infinity, right? So this is equals to 2 alpha square minus 4x transpose 0 to infinity rs ds. Okay, so this is something we know that theta alpha, the final point satisfied. Maybe let's call this equation 2. And then we also know that x theta alpha is equals to y, because we assume, or we can prove, I guess we discussed this. I think we can prove that you converge to a feasible solution. So, and I'm claiming that 1 and 2, so 2 and 3, these two things turned out to be the optimality condition of the program of the program. Let's call it 1. So 1 is this arc-mean thing. Okay, I guess it's far away. So here, let's call this program 1. Right, so you want to say that theta alpha is the minimizer of this program 1. And it turns out that theta alpha satisfies these two equations, 2 and 3. And these two equations are the optimality condition of that optimization program 1. So, and that optimization problem only has one solution because it's convex. So that's why this theta alpha is the solution. That's the plan for the next. Right, sounds good. So by optimality condition, I really mean the KKT condition. So I'm not sure whether all of you are familiar with the KKT condition. So I guess there are two ways to think about this. This is just a small thing about background about KKT condition. So these are optimality conditions for constraint optimization problem. To be honest, I never really remember exactly what's the KKT condition in many cases. So what I'm going to show you is that one way to think about it. So which is probably not exactly the same as what you're going to read from the book, but it's going to be very similar. So suppose you have this kind of things, right? Optimization program like this, and Q theta is a convex thing. And so first of all, the KKT condition is the following. So it says that Q theta is to be equals to X transpose V for some V in dimension, I think this dimension is N, and then X theta needs to equals to Y. So this is the KKT condition for this kind of program. And one thing you can do is you can just look up a book and like just invoke a theorem from a book which says that this is the KKT, the optimality condition. The way I think about it is the following, if you're interested in it. So the way I remember this is that I derive this every time if I need it, as follows. So I think that the insight is that optimality at least means that there's no first order update. There's no first order local improvement. So if you perturb your solution, you shouldn't have a first order improvement locally. If you perturb your solution locally a little bit by an infinitesimal small amount, you shouldn't get a non-trivial first order improvement. So but you also have to satisfy the constraint. So you also like no first order local improvement satisfying the constraint. Satisfying the constraint also up to first order, because you may not be able to. So what does this mean in this case? It means that suppose you consider perturbation delta theta, right? This is a perturbation. So how do you satisfy the constraint? To satisfy the constraint, you have to say that the perturbation needs to be in the orthogonal to the row span of X. Because if it's not in the row span of X, you perturb it, you may change the X theta, and then you change the you don't satisfy constraint anymore. So this is the way to satisfy constraint, so that so that X delta theta is 0. So that's how you make the constraint work. And now let's look at theta plus delta theta, the local perturbation. And so this still satisfies the constraint, and let's see what's the value. So let's see what's the value of Q. So Q theta plus delta theta. This is equals to up to first order Q theta plus delta theta times.
Hi, Professor. We cannot hear you.
Maybe let's try this. Can you hear me now? Thanks for letting me know.
Yes, I can. Thanks.
Is the audio good or not? Is it okay?
Yeah, it's okay.
Okay, so I'm using my laptop's microphone, so maybe let me turn it in some way so that it will work better. Yeah, thanks for letting me know. So maybe I'll rewind a little bit back. I don't know how long time you have lost me. So I guess maybe I'll just briefly go through the steps that we have discussed. So I guess I was saying that if you have the perturbation, you always satisfy the constraint, right? If the perturbation is the row span of X, is orthogonal to the row span of X, then you always satisfy the constraint. And we want to understand, we want to figure out under what condition this perturbation will never improve your function, will make the function bigger. Because if it makes the function bigger, it means that this point is not optimal. So that's why you look at the Taylor expansion of of this Q, and you found out the first order changes is this term, and you want this term to be always non-negative, non-positive, because if it's positive, then it violates the optimality assumption. So it's a necessary condition is that this term is always non-positive, but this term, it's very easy to make it the sign flip because you can use the flip delta theta by whatever sign you want. So that basically means that for every delta theta in the orthogonal space of row span of X, this term has to be just literally 0, because if it's not 0, you can flip delta theta to make it positive. So that's why we are saying that here, for every delta theta in a row orthogonal to the row span of X, this term is 0. And that really just means that this vector, so because every delta theta in a row in this subspace is orthogonal to this vector, that means that this vector is in a complementary subspace of the subspace of delta theta. So that's why this vector Q theta needs to be in the row span of X, so that for every vector delta theta orthogonal to the row span, their inner product is 0. So that's why it can be written as X transpose times mu, because X transpose gives you the row span, X transpose mu, X transpose, I think let's call it V. X transpose V is the representation of a vector in the row span of X. So that's why that's how we develop the KKT condition, right? The KKT condition was that you have to be in the row span. The gradient of Q at theta has to be the row span of X, and also it has to be a feasible solution. Okay, cool. So this is some digression about KKT conditions. If you're not familiar with it, then the only important thing is that this is the characterization of the optimal solution at theta. And we can, now it's just a pattern matching, right? So this corresponds to this, right? Obviously, and this one really just corresponds to equation 2, because equation 2, okay, that's what I'm going to claim. Okay, it's not trivial yet, but let's see that. So KKT tells you that the gradient of Q theta needs to be something like X transpose V, and the invariance or the differential equation tells us that, let me just copy paste it. Let me just rewrite it. So theta alpha is equals to 2 alpha square sin. All right, so first of all, let's rewrite this as, to simplify this, and rewrite this as times V times maybe V prime, let's say, because the V, what V is doesn't matter. And then you can I guess let's also work on the Q theta thing. So delta Q theta, you can compute this. In some sense, when you derive the Q, we are verifying it, but actually what you have to do is to reverse engineer to do this in the other direction. But if you just verify that, suppose you are given a Q, if you just want to prove it, you can find the derivative of the Q will be just arc sinh 1/2 alpha squared times theta. This is the derivative of Q. It makes sense because the Q is a sum of some function of theta I, and the derivative of Q is each entry is some function of theta I. And so then you can see that this, if you plug in the theta alpha here to this thing, so arc sinh alpha squared theta alpha, this is equals to just the 4x transpose V prime, right? So that's why. So basically that's why gradient Q theta alpha is equals to minus 4x transpose V prime. And this satisfies the KKT condition. The 4 doesn't matter because the V can be any vector, right? So that's why Q alpha satisfies the KKT condition. And we are done. So it's the global mean. It's the global mean. I guess to this last step, satisfying KKT condition means global mean. This requires the convexity of this program. The constraint is linear, is convex. The objective, you can verify it's also convex. It's something between L1 norm and L2 norm. Both of them are convex. Any questions? So if there's no questions, I'm going to move on to the next thing, which is about classification problem. Yeah, I see many of you are staring like this proof still. Like this proof, I don't know. I don't have the plan sounds very intuitive, right? So how do you prove something is the minimizer of a optimization program? You have to verify it satisfies the KKT condition. I guess that's probably more or less the only way to do it. If you want to show something is the optimizer of some optimization program, but it's kind of the magical why it just happens to satisfy the KKT condition. So of course, there's something that we can choose, right? We can choose the Q to make it satisfy the KKT condition. That's something you can choose. But the magical thing is that other things all match up, like the form, the X transpose times something. All of those things are matched up, and also you can somewhat, in some sense, you can always work with each coordinate independently in this special case. So that's also something that may be a little bit special to this special model that we consider. All right. Okay. So now let's move on classification problem, and we are looking at separable data, as we always do for classification problem, and here we are going to only discuss one result, and which says that if you do gradient descent, it converges to a max margin solution, and this is actually doesn't require any initialization. Like it works for any initialization. Like so the only thing you need is gradient descent and some loss function, which I'm going to define. And no regularization, you just compute gradient descent on the loss function, you run for a long time, you're going to converge to the max margin solution. So I'm going to have, again, start with the setup. So now we have a data set xi, yi, and from 1 to n, and xi are in RD, and yi is a binary label, +1 - 1. And sure.
About the setting, basically.
Okay.
So if instead of assuming the form to be W squared,
okay,
it's W to the power k, then the rest of the proof is not carried through because it breaks down that, like when you compute the derivative, then you can't get like the next close form to differential equation.
Okay, yeah, so the question is about the previous thing, and the question is about if you don't use W square, you use W to the k. And this is a very good question. Actually, this is exactly what the paper studied in the more technical part. So, and the short answer is that everything can still go through, and but the eventual Q would be different. So the form of your Q would be something not L1, L2. I think it's something like L. It depends on the power. So I think if the power is P, I don't exactly remember, but I think it's something like 2/P norm when alpha is close to 0. When alpha is going to infinity, I think everything is still the same. Like the NTK regime is not sensitive to this. Technically, why everything goes through? I think the reason why everything goes through is that, roughly speaking, you are only playing with this single-dimensional function in some sense, right? So it won't be sinh anymore. Probably there will be some constant, some other function, but still this X transpose something is still there. I think it's not changed, and so eventually you just have to engineer a different Q to make everything work, and the Q is still kind of only depends on the coordinates, right? You do something on each coordinate, you take the sum. The Q still has this form. So that's why it's still somewhat doable. Okay, cool. So going back to the classification problem. So this is our setup. And here we're only going to do the linear model, even though some of this theory still works for nonlinear model with roughly similar technique and similar conclusion. And here we're going to have a loss function. So the loss function will be L hat W is the let's say we do the cross entropy loss, the logistic loss, and the cross entropy loss times HWXI and where this loss is this logistic loss, which is log of 1 plus exponential minus t. Okay, cool. So, and the first thing is that to kind of like get some intuition. So first of all, we have multiple global mean if separable data. So this is a premises for any implicit regularization effect, right? If you only have one global mean, then and you can converge the global mean, there's no implicit regularization effect. So, but why there are multiple global mean? This is just because you can always have like a infinite number of like separators, pretty much, unless in a very extreme case you just happen to get stuck at exactly. So for example, I think it's probably easier to draw something. So suppose you have some data points like this, and you have so many different possible separators. As long as you have one, you perturb it a little bit, it's still a separator. So there is the infinite minus W such that W transpose Xi, Yi is bigger than 0 for every I. So you have so many separators, and for every W, for maybe let's say for infinite number of W bar such that where W bar is unit. W bar is unit vector. This statement doesn't really depend on the norm, so you can always scale it. So for every W bar, for any W bar such that this, you can scale it. So if you look at L hat alpha W bar, so we'll go to 0 as alpha goes to infinity. So any scaling of this unit separator, if you scale it extremely, then you are gonna get the loss goes to 0. So basically, you have so many directions in it, so you can go to infinity in different directions, and still converge to a 0 loss. So basically, in some sense, if you are a little sloppy about, so all of this infinity times W bar are global minimum of this loss function, just because the loss function goes to 0 at infinity. Right, so the loss function, maybe I should also draw this. The loss function looks like this. This is the L of t. When t goes to infinity, you get close to 0 loss. And what's inside, what's t? T is y times W transpose Xi, and this thing will go to infinity as you scale the norm of the classifier. So you have so many directions that you can find. There are so many global minimums. So the question is, which direction will you find by gradient descent, right? if you don't use any, if you just invoke a theorem about optimization, you know that gradient descent will find a solution with error close to zero, with loss close to zero, but you don't know which direction it is. You still have a bunch of flexibilities. Right? Many directions can, if you go to infinity in many directions, you can get the loss to get to zero. So that's the question that we are trying to address. So, and we're going to say that this actually converges to max margin solution. So let's define, so the answer is max margin solution. Direction. So I guess let's define maybe first the marginalized, the margin and the normalized margin. So I guess we have defined the margin in this class many cases, whereas in many cases, the margin is the minimum this. And we also assume, okay, so we always assume linearly separable. So this definition is only defined for cases where it's linearly separable. And a normalized margin is defined to be, you normalize this by the norm of W, because otherwise you can make the norm arbitrarily big or arbitrarily small. Okay, so max margin solution is defined to be the, for all W, which one give you the maximum normalized margin. And let W star be the maximizer. This is the direction of the max margin solution, and with unit norm, because if you only look at this objective, it doesn't depend on the scale, because the scale is already normalized out. So we define the W star to be the maximizer with unit norm. Okay, so basically we're going to prove that if you do gradient descent, you're going to go to infinity. The iterate will go to infinity, but only along the direction of W star. That's the theorem. So gradient flow, I guess here we're talking about gradient flow just because it's convenient, as we discussed. So convert this to the direction of max margin solution. In the sense that I think we don't really exactly say the convergence in direction. We only say the convergence in the sense of like the value of the margin. I think really you want to do the exact convergence in direction, it requires a little more work. So what we say is that the margin of your iterate will converge to the maximum possible margin, gamma bar. Right. So as t goes to infinity. So, and WT is the iterate at time t. I think I have 5 minutes. So in the next 5 minutes, I'm going to discuss a little bit about the intuition, why this is working. This intuition contains why this is working and how do we prove it in some kind of a mixture of both of these two. And then in the next lecture, I guess I would prove the thing more rigorously. So why this is working? So the intuition is that, so I guess I have a few steps here. So step one, this loss function, L hat WT is going to 0 by standard optimization argument, which is not covered by this course. So, but I think you can kind of believe it. If your optimization is working, then your loss should go to 0. And second, so this is observation 1, and observation 2, I guess the loss, this loss function, which we define to be the logistic loss, right? Something like this. This loss function is actually close to exponential for large C, right? This is just because you do Taylor expansion, right? Log of 1 plus x is approximately x. That's why you can get rid of the log and 1. And this is actually an interesting thing, right? So you call it logistic loss, but actually it's close to exponential loss. So like so logistic loss is close to exponential loss. So in most of the proof, actually, we are only going to do the logistic loss. I think in the proof, actually, I'm just going. Sorry, I'm going to do the exponential loss. So in the proof, I'm going to just assume it's exponential. Even though you can still, these small differences can be dealt with relatively easily. And the third observation is that because of one, the WT has to go to, the norm has to go to infinity. And the reason is that if you just don't go to infinity, you never make the loss close to 0 enough, right? This is just because if WT is bounded, however, let's say it's bounded by B, suppose it's always bounded, then you can always bound this yi times W transpose xi by something like maybe B times the norm of xi. You have some bound, so this is bounded. And then your loss, L height WT, this is, bounded by exponential minus B times xi, something like this. And this is bounded below by 0, and this contradicts with 1. Right. So if your norm is always bounded and your loss is bounded below by some number, the number is very close to 0, but still is bounded by some number which contradicts with the convergence to 0. So now it comes to the most important thing. So with all of this preparation, so we know that the norm goes to infinity, and then suppose let's only look at the final case, the later regime where WT is really big. So suppose WT2 norm is really big. That's called Q is very big. So then let's try to simplify the loss function and see what the loss function is trying to do. So the loss function, maybe let's remove the T just for simplicity. Let's just look at, suppose you only look at some W such that the W norm is very big. So then L hat W is the sum of this logistic loss or exponential loss. We're not distinguishing for now. And this is, let's say this is roughly equals to the exponential minus yi times W transpose xi. And because the loss will be very close to 0, it's actually more informative to look at the log space. So if you took the log space of L hat W, then this is roughly equals to the log of sum of exponential minus yi times W transpose times xi. So this is a log sum exponential. I'm not sure whether this will bell to some of you. So this is basically softmax. So I'm going to claim that this log sum exponential is close to max of this. Minus this. Yes. So why this is the case, let's do some, again, abstract derivation. I guess I'm running late. So if you have log, okay, I guess, sorry, I think probably I should have another step. So let's first another step. So this is log sum exponential, but also I can try to, I want to use the fact that W has large norm, right? So let's get the norm of WQ in front. You get YI times W bar transpose XI, where W bar is equal to normalization of W. Okay, so now I'm going to claim that this is close to max minus QYI W transpose XI, I over. So why this is the case, this is, I guess, from those who are familiar with this, log sum exponential is kind of like a soft max. So if you look at log sum exponential of some, let's say Q times UI, I'm trying to kind of like abstractify a little bit, right? So you have a Q that is very large and UI is something fixed. I claim that this is close, this is roughly Q times the max of UI, I in N, plus something like little of Q, something that doesn't depend on Q as much as Q goes to infinity. So when the Q is very big, then this is really doing a max. And sometimes this is kind of like when you do a temperature in the soft max. If you make it big, then soft max becomes hard max. So and if you do then this is really in sometimes soft max. And this is, if you want how to prove this, just say the sum of exponential QUI with proper upper bound. The upper bound is that it's the log of, replace each of this by the biggest one, exponential Q times the max UI. And this is only log N plus Q times the max of UI. And so the log N is small compared to Q because Q will go to infinity and N is something fixed in this abstraction. And on the other hand, you just take one term. You just only keep the term where you have the max, then you get Q max UI. Or you drop all the other terms, there's no sum anymore. The log cancels with exponential to get this. So basically, this log sum exponential is close to the max up to some factor log N, but this factor log N will be small if Q goes to infinity. And that justifies this step, right? So, and once you have this step, this, what's going on here, right? So this is saying that you are minimizing the you are minimizing the loss, so that's why you minimize the log loss as well, right? So minimizing loss is kind of like trying to maximize this, and that means you are maximizing the, so you are trying to minimize this quantity, minimize the quantity max minus QYI W transpose XI, which means it's the same as maximizing, which means that, so you are minimizing, but you are maximizing the mean of QYI W transpose XI. Right, so you just flip the sign, right? Minimizing the max of this is the same as maximizing the mean of, this is just literally the same here. Like without any, it's not like you're switching mean and max, it's just really the sign. You have the minus sign, maximize something is the same as, the max of this is equals to the minus the mean QY W transpose XI. And then you can put this minus outside the minimize. Okay, so all right. So basically, you are maximizing the margin. That's what this is saying. So if you do this approximation, then you are maximizing margin if Q goes to infinity. And next time we're going to make this more formal, with a little bit, with essentially the same intuition, but the proof, would be more clean. It's not exactly like this. It's not like you're dealing with errors. Like it's going to be a very clean proof. Okay, I think that's all for today.